right? So we've had some deliberations on motion, starting from position to velocity and to acceleration and so on and so forth. And we looked into the gist of one-dimensional motion, extended its wings to two-dimension, and of course, an extension into the third dimension would be no new story. The same thing extended to just another dimension. It'll look very routine and mundane. So, what we've examined is motion. We've not examined what causes it. There are laws of nature. Essentially, when I talk of laws of nature, I precisely mean an interaction or connivance between two kinds of things. One, properties of bodies, particles, and properties of the surroundings. When they get stitched on the same fabric, it leads to enunciation of laws of nature. Needless to say, what dawns upon us in the form of Newton's laws was not just the work of a genius, it must have been the work of God. It couldn't have come out of intellect, it must have come out of inspiration. One of the things that we're going to keep deploying in physics is what's referred to as abstraction. Now, suppose there is an aeroplane flying at a certain height. Above the surface of the earth. And I want to find the force that this aeroplane experiences out of its gravitational attraction with Earth. Then I carry out the following stuff. Number one, I imagine the Earth to be perfectly spherical, with the mass concentrated at the center of the Earth. I imagine the aeroplane to be a point particle, and so on and so forth. Now, in the process, hosts of assumptions. And these assumptions get packaged into what's called abstractions. These abstractions lead to errors, semblance of errors. Or in fact, errors. Why even semblance of errors? They actually lead to errors. But then, the extent of errors produced out of abstraction does not bother us enough. We can live with those errors for the sake of practical wisdom. It's fine. The extent of errors produced out of abstractions can be accommodated. When we talk of a particle moving on a frictionless surface, a smooth surface. First of all, there is nothing like a particle. You can never have a particle because a particle is a point. You can't have a point as a particle. You can't really have. But then that's part of an overall abstraction. When you talk of the particle moving on a smooth surface, now that smooth surface, is it reality? Can you actually have a smooth surface? You cannot have a smooth surface. You can't have a frictionless surface. But again, what it really means is that the particle is subject to many other forces, and those forces are much larger compared to frictional forces. And therefore, the surface could be imagined to be smooth for the sake of practical considerations. So that's an abstraction. So, an abstraction will lead to errors, but that's fine. Not an issue with all of it. Now, very often I'll talk of what's called a frame of reference. When I talk of a frame of reference, then what I essentially mean is a coordinate system. The x, y and the z axis with an origin orthogonally defined. Refer to that coordinate system. I'm going to measure positions. I'm going to measure velocities. I'm going to measure accelerations. So that coordinate system would essentially be our frame of reference. We're going to commonly talk of certain kinds of forces. It's important for us to understand the basic traits and characters of these forces. We'll talk of contact forces. We'll talk of contact forces which arise when two bodies are in contact. And let's say this is one body and this is another body. These are two bodies in contact, A and B. Now, contact forces in general would have two constituents or two components. For the bodies in contact, there is a common surface, for example. In this case, there is a common surface. There is a normal direction, which is this. This is a normal direction, perpendicular to the two surfaces. Then these two bodies exert on each other contact forces which would have components in a direction perpendicular to the normal direction, which is the tangential direction. A direction perpendicular to the normal direction is the tangential direction. They would exert forces on each other in the tangential direction and in the normal direction. The force that they exert on each other in the tangential direction appears to us in the form of what's commonly known as friction, frictional force. Along the tangential direction, the forces that two bodies exert on each other is the frictional force. And the forces that they exert on each other in the normal direction is a normal force, is commonly referred to as a normal force. So contact forces would have two constituents. They would be a normal force and the normal force would be in the direction perpendicular to the surface, and a frictional force which would be along the tangential direction. Frictional force which would be along the tangential direction. And both these forces, normal forces and contact forces down the line, we learn are essentially electromagnetic in character. These forces are electromagnetic in character. The charges on the two bodies are responsible towards production of these forces, electromagnetic in character. Now, when I talk of a contact force, with one being a normal force, one of the constituents of the contact force is a normal force. If the two surfaces are frictionless or smooth, then the tangential force, that is the friction force, vanishes. practically zero. But then, when I talk of a normal force, suppose this is a surface. This is a surface. And this is a body resting on a surface. This is a body resting on a surface. Then the normal force that the body exerts on the surface, and therefore the surface exerts on the body, in this case, is perpendicular to the surface. The surface would exert on the body a force N. The body, as a consequence of Newton's third law, would exert on the surface an equal and opposite normal force. It's a measure of the extent to which two bodies are pressing against each other. The extent to which two bodies are pressing against each other is measured by the normal force. Now, one basic trait of a normal force is that normal forces acting on bodies or on surfaces would always push, will never pull. Normal forces will always push. Will always push. For example, on the body, the normal force is like this. This was the body, this was the surface. So on the body, it has a tendency to push the body. This was the force that the surface is exerting on the body. So this force is acting on the body. And who's causing it? The surface. As far as the surface is concerned, the body as a consequence of the reaction will exert on the surface an equal and opposite force N. So then, this N is pushing the surface, this N is pushing the body, right? So normal forces, the direction of normal forces would be examined based on pushing characteristics. They will always push. I mean, the surface will never exert a force on the body in this direction, because that will tantamount to pulling. I hope you have a very clear distinction, transparent understanding of pushing and pulling, right? So, the surface cannot pull the body, it will only push the body out of its normal forces, right? So, normal forces would always be pushy in character. Now, there are various ways in which the normal forces could act on a body resting on a surface. Suppose there is a surface and there is a body which is resting on a surface. This is a situation, let's say on the body, this is the body and this is the surface. The normal force on the body in this case would be perpendicular to the surface as well as the body. This is perpendicular to the surface as well as the body. Now, we can have a different kind of a disposition for normal forces. Suppose this is a wall, and this is the floor, and there is a ladder. There is a ladder resting. Now, the normal forces would obviously act wherever there is contact. The normal forces would act wherever there is contact because they arise out of contact. This is a ladder resting against a wall. Now, if somebody says, what's the direction of the normal force acting on the ladder? What's the direction of the normal force acting on the ladder? First of all, the normal force on the ladder would act at A and B both, right? At A, the normal force would be perpendicular to the surface. This is the surface and this is the body, right? Would act perpendicular to the surface but not to the body. This is the body and this is the surface. In this case, the normal force is acting perpendicular to the surface but not to the body. At B, the normal force experienced by the ladder again would be like this, where it's perpendicular to the surface but not perpendicular to the body. It's perpendicular to the surface but not perpendicular to the body. In this case, it's perpendicular to the surface as well as the body. You could have had, let's say, if there was a surface like this. There was a surface like this. And if the ladder were to be resting this way, if the ladder were to be resting this way, then the points of contact are A and B. Now, at B, there is no ambiguity. At B, there is no ambiguity. The normal force on the ladder at B acts in a direction perpendicular to the surface. At A, when it's time for the normal reaction to act, the normal reaction gets terribly confused. It gets very confused. Why does it get confused? It faces a very peculiar situation. It does not know whether to imagine AX to be the surface or AY to be the surface. The normal reaction, on one hand, thinks AY is the surface. If AY were to be the surface, then the direction of the perpendicular to the surface would be like this. If AX were the surface, then the direction of the perpendicular is like this, right? So then, and both AX and AY are insisting, hey, be perpendicular to me, hey, be perpendicular to me. So then, the normal reaction needs to take a quick decision. It says, I can't oblige both of you. You can keep fighting. I'll oblige the ladder. It obliges the ladder in this case. It says, okay, neither AX nor AY, it's time for the ladder to pitch in. I'll be perpendicular to the ladder. That means in this case, it's perpendicular to the body but not the surface. It's perpendicular to the body but not perpendicular to the surface. Right? So it could be perpendicular to the body as well as the surface, perpendicular to the surface but not the body, and perpendicular to the body but not the surface. So all possibilities could exist. Clear? Also, let me tell you that this normal reaction need not necessarily act through the midpoint of this body. I mean, there is a normal reaction at every point, and the resultant of all these is a single force and acting upwards. And its line of action need not necessarily be the midpoint. It could be shifted leftwards. This could be a non-uniform body, for example. If it's a non-uniform body, then the net normal reaction from the surface need not be the midpoint. Or we'll realize down the line that, let's say, if there is an additional force F acting on the body, then the line of action of the normal reaction would shift from its midpoint. We'll look into why that happens. So, it's not essential for normal reaction. It's not essential for normal reaction to act through the midpoint, The other thing is that the normal reaction is a self-adjusting force. The surface would exert on the body the normal reaction that is required. We'll see what would be grounds for action of normal reaction. But then it's like a self-adjusting force. It will determine its own value depending on the situation, right? Again, the other kind of force, which is not a contact force but is action at a distance force, is the gravitational force. The force that Mother Earth exerts on a body. Now, in this case, Mother Earth exerts on the body a force mg downwards. The Mother Earth exerts on the body a force mg downwards. And this n and mg are independent forces. This n is the force that the surface exerts on the body, And this mg is the force which the Mother Earth exerts on the body. They're coming out of two different sources. They're not coming out of the same source, right? They're independent forces. And it's not like n would always be equal to mg. For example, if this body is in a state of equilibrium, then the net of all forces in the vertical direction is 0. Then we have n because of the surface minus mg because of the earth turning out to be 0. But suppose this was a surface, let's say a platform kind of a thing, and a body of mass m was resting on it, right? And this platform was given an upward acceleration a. Now, the forces acting on m, there would be normal reaction from the surface, and there would be mg acting downwards because of Mother Earth. The net of all forces. So these are the causes. This is the cause. The forces are the cause. The acceleration is the effect. Which means now the net of all forces in the vertical direction is n minus mg. After all, for this body, what is causing the acceleration a? For this body, just the mass m. The cause of acceleration is n minus mg. In this case, n minus mg is m into a. So n now is no longer mg, as you can say. N is m into g plus a. Yes or no? Or you could have had a situation like this, in which the platform has a downward acceleration a, and this body of mass m rests upon this platform. The forces acting on m are n and mg downwards. Now, as far as m is concerned, it has an acceleration a downwards. And what's the cause of its acceleration? The resultant of mg and n. That means mg minus n is ma. So n then is like m into g minus a. And realize that n could actually be equal to 0. Now, what does n equal to 0 mean? In physics, the mathematical description of contact between two bodies. How does one know? In the larger scheme of things, if two bodies are in contact, two bodies would be in contact if the normal reaction is greater than 0. Two bodies in contact would mathematically be represented by n greater than 0. N greater than 0 would be a representation of two bodies in contact. The mathematical representation of two bodies in contact. For two bodies in contact, the normal reaction between them must be greater than 0. The normal reaction between them must be greater than 0. What would designate loss of contact? N equal to 0. After all, if there is no contact, how would there be normal reaction? N equal to 0 would designate loss of contact. In physics, loss of contact is represented by n equal to 0. N equal to 0 represents loss of contact. N greater than 0 represents contact. Clear? In fact, suppose this is a body of mass m resting on the surface. There is mg acting downwards, and somebody presses it with a force F. Somebody presses this against this. Let's say this surface is fixed. and somebody presses the surface with a force F, right? The normal reaction will no longer be mg. We, as a revised condition for equilibrium in the vertical direction for the body, we have like a F plus mg equal to n. F plus mg equal to n. So the normal reaction gets revised. The net downward force equals net upward force. F plus mg equal to n, right? So then the normal reaction gets revised, right? That's when I said it's a self-adjusting force. It's a self-adjusting force. If this body was resting on the surface and this surface was fixed, the surface exerted on the body a normal reaction N and weight mg downward, right? And this body was unaccelerated. What's the net of all forces acting on the body? N minus mg. What's the acceleration that it produces? 0. Mass into acceleration. Net force. So N becomes equal to mg, right? Now, so two kinds of forces that we have looked into. One is the normal reaction. The other one is action at a distance force, which is the gravitational force mg, which is out of gravitation. The third kind of force is the force that appears in strings. The force that appears in strings. In physics, we'll encounter two kinds of entities, strings and springs. Strings and springs. To draw a distinction between strings and springs, just one thing that you need to take care of. A string is an inextensible entity. A string is an inextensible entity, whereas a spring is extensible. A spring is extensible. The length of the spring could change, but the length of a Hello. Yeah, so coming back to your question. Hello. Coming back to these two entities in all of mechanics that we're going to encounter, strings and springs. Like I said, a string is characterized by its inextensibility. Again, that'll be part of an abstraction because you can't have a perfectly inextensible entity. Every entity would actually, so that's a good enough approximation, so to say. So you have strings that are inextensible, and there are springs that could be extended, that could get deformed under the influence of a force. Now, in strings, the forces that we encounter in strings are referred to as tension forces. Now, suppose this was a wall and there was a string. There was a certain string. Let's call the string AB. And if you apply a force F at B, if one applies a force F at B, then what really happens is there are forces again, those are also electromagnetic in character. There are forces that build up inside the meat of the string. At any given point P, you can associate a certain force T. Any given point P, you can associate a certain force G. What does this T imply? This T really means that if this force is T, then this T actually exists in both directions at P. There is a T like this and there is a T like this at P. This T really means that this force is in both directions at P. But then what does it really mean? It means that if you ask AB, suppose AB had a mind and AB could speak, alright, and if you asked AP, is the string pulling you with a certain force? If the string pulling you with a certain force at P, then this will say, yes, I'm being pulled by this force T. AP would report that it's being pulled by a force T acting to the right. That means this T would act on AP at P. This T, see, like I said, there is T in both directions at P. But if you ask AP, then AP will say that I'm feeling this T. AP will feel this T. It will be pulled by this T. If you ask PB, then PB will tell you that I'm being pulled by this force T. There is T in both directions at P, but this T is experienced by AP and this T is experienced by PB. Right? Which means, again, there is tension in both directions at P, but AP and PB would report different directions. AP will tell you, I'm being pulled. PB will also tell you that I'm being pulled. And both will report that they are being pulled by the same force T. And this is the force of tension. Both sides of the same point would experience the same force, same magnitude of the force because of tension, the force at that point. But then the direction of this force would always be pulling in character. Tension at a point, acting on a body or an entity. Write down, tension at a point, acting on one of the entities, would always pull that entity, Tension will never push. For example, suppose there is a string and there is a mass m hanging at one end of the string. And if you had to find the tension at this point, the tension at this point will act on m. The tension at this end will act on m. And it will always want to pull m. Tension at this point would act on the ceiling and would always want to pull the ceiling. The force because of tensions will never push. They will always Now, having said this, Even before I make more remarks on all of this, let me tell you that in almost all of mechanics, we would, in all situations, have the first task of summarizing forces on a body or a collection of bodies. The summary of all forces, yes. Now that's another story. That will depend on the mass of the string, whether it has mass or not. I'll just come to that in a few minutes from now. Whether T was equal to F, or under what conditions T was equal to F, under what conditions T was not equal to F, I'll digress in a while, right? First of all, right now, all that I want you to understand is that in the meat of a string, in general, you can expect a certain force to exist at any point. That force would act in both directions. The implication of that force is that on one side of that point, there would be one direction of that force. On the other side of that point, there would be the direction of that force. And that force would always be pulling in character. I mean, like in this case, this was the point P, and I said there was tension T like this, and there was tension T like this. Right? And if you ask this entity, if you inquire this entity about the force acting at P, if this was the entity, this was AB, and you just took part of AB around P, this one, XY, right? If you took this length of the string and you ask this length, what is the force at P? If you ask this length, XY, what is the force at P? Then this length will tell you the force at P is T minus T, which is 0. This length XY around P will tell you that the force at P is not T, but will tell you it's T minus T, which is 0. However, like I said, the length AP will tell you that it's being pulled with a force T rightwards. The length PB will tell you that it's being pulled with a force T leftwards. Such is the trait of this force, tension force, right? But if you inquire XY and said, what's the force at P because of the string? It'll say 0. Because this will witness a T like this and a T like this at P, and the net of these two T's at P would be 0. This T acts on AP, whereas this T acts on AP, whereas this T acts on PB. That's what happens. Clear? Now, we would time and again, or rather almost always, summarize forces acting on a body or a collection of bodies. And the summary of all forces acting on a body or a collection of bodies is called a free body diagram. Summary of all forces acting on a body is called the free body diagram. It's called the free body diagram of the body. FBD. We would commonly designate it with this abbreviation FBD, free body diagram. Now, suppose there was a mass M and there was a force F applied on this mass M. And you were asked to draw the free body diagram of small m alone. Then you would isolate free body diagram of small m alone, means you'll isolate M from the wall. The moment you isolate M from the wall, you would have to include the effect of the wall when they were together. I mean, isolating a body from another body, you would have to pay a price for it. What's the price? You must make sure that the effect of that body in terms of forces is accommodated and accounted for. That's what it means, right? So, the moment you're isolating the body, it's not like you're strictly isolating that body. You're isolating the body and you're incorporating the effect that other bodies had on it when they were together. right? So what was the other body that was in contact? The wall and the floor, right? So isolating it from the two means, first of all, there was a force F acting on it. There was a force F acting on it. Which was external? Irrespective. Now, when this was being pushed against the wall, then the wall was exerting a force, a normal force on M, leftwards. And like I said, the normal force will always be pushing in character. So the wall exerted on M a normal force N. The wall exerted on M a normal force N to the left. Now, this takes care of the presence of the wall because I'm including the effect of the wall. If I'm isolating it with the wall, I'm including the effect of the wall, right? Now, if I'm isolating it from the ground, I must include the effect of the ground. The ground exerts on it a normal reaction upwards, right? So, the effect of the ground is represented by R. Now, I can separate the ground. Now, I can separate the ground because I have included the effect of the ground, right? And there is mg anyways, the effect of the earth, gravitation. So this is the free body diagram of small m. This is the free body diagram of small m. If then you are asked to draw the free body diagram of the wall, then well, that means, after all, the wall, the floor and the mass were one unit. And now you're drawing free body diagrams of the various constituents of this unit, right? So one constituent was this, whose free body diagram is this, right? The other constituent, now as far as the wall is concerned, if the wall exerts on M a normal reaction N leftwards, then the body will exert on the wall an equal and opposite normal reaction, which is N rightwards, right? So the body exerts on the wall a normal reaction N rightwards, right? Now, for the ground, as far as the ground is concerned, well, M exerts, or rather the ground exerts on M a normal reaction R upwards. So M will exert on the ground a normal reaction R downwards. So this is as far as the ground is concerned. Now, if somebody just said, draw the free body diagram of M and the wall. That means now I'm including the wall in the free body diagram of M and the wall. If M plus wall, M plus the wall, that means now I'm regarding M and the wall as one system, Then, at the interface of the wall and M, they exert equal and opposite forces on each other. So, if this was one unit, then the N that the wall exerted on M and M exerted on the wall, they would cancel off in pairs, N and M. Because now, this N, if the wall was part of the system, then this N would become an internal force. And they would cancel off in pairs. So then, the representation of N will not take place if M and the wall were cemented together, regarded as one unit. But if M was isolated, or if the wall was isolated and represented, then the forces that they exerted on each other must be delineated when isolated. The effect of each other must be represented the moment you create an isolation, right? So that's a free body diagram, the summary. So it depends on whose free body diagram you are drawing. Now, suppose we had a system like this. Let's say there were two masses, M1 and M2, and let's say they were resting on a smooth surface. Right. And a force F was applied on M1. Fine. And now we are asked to draw the free body diagram of M1 and M2. Free body diagram of M1 and M2. Now, when I have to draw the free body diagram of M1 and M2, then I don't have the headache of representing what they are doing to each other at their interface. Because whatever they are doing to each other at the interface is now an internal story between them. That does not require representation on M1 and M2 put together. What they exerted on each other at their interface does not require representation, should not be represented. That then becomes an internal force cancelling off in pairs. Which means now, what are the external forces acting on M1 plus M2 as one system? On M1 plus M2 as one system, there is like a M1G acting downwards, Mother Earth. There is M2G acting downwards, Mother Earth, right? Then the surface. Don't get confused. The surface exerts on M1 a normal reaction R1. The surface exerts on M2 a normal reaction R2. Yes or no? So this is the free body diagram of M1 and M2. What does not find representation here? What M1 and M2 are doing to each other. They are part of one cohesive unit. Their impact on each other cancels off when they are represented together. There is no net external influence when they are present together. That's an internal force which would cancel off in pairs, right? But now, if I said, draw the FBD of M1 alone, draw the free body diagram of M1 alone. This is M1 and M2. M1 alone. That means now I am detaching M1 from M2. The moment I detach M1 from M2, I would have to include the effect that M2 had on M1. And they influenced each other to the tune of normal reaction between each other. Right? So, M2 exerted on M1, after all, the normal reaction that M2 can exert on M1 would have to be like this. It can't be like this. Normal reaction cannot pull M1. It will only push M1. So, the direction of the force that M2 exerts on M1 must be leftwards. The normal force that M2 exerts on M1 must be leftwards. N is the normal reaction that M2 exerts on M1, which is leftwards. There is an external force F anyways, acting on M1. Then there is gravity, M1G downwards. And there is normal reaction R1 from Earth upwards. Not from the Earth, from the surface. From the surface. There are two different things. Right, from the surface, R1 upwards. That's a FBD of M1 alone. Now if I have to draw the FBD of M2 alone, this is M1 alone. This is M1 and M2. And now if I have to draw the free body diagram of M2 alone. So now, look, as far as M2 is concerned, it doesn't even know of the presence of F. The presence of F is indirectly communicated to M2 by means of the force that M1 exerts on M2 in the form of a normal reaction, right? So, the data related to F remains concealed from M2. M2 only knows of the force that M1 exerts on it in the rightward direction in the form of normal reaction. If M2 exerts on M1 a leftward N, M1 will exert on M2 a rightward N. So the presence of F is built into this N. But the value of F is not known to M2. It will only know of N, it will not know of F. Right? And then there is gravity acting downwards, M2G. And there is normal reaction, R2 acting upwards from the surface. This is the FBD of M2. Now, one very important thing is that, so what we have really is like a M1 and M2 as a system whose constituents are M1 and M2. This is one system, one unit with constituents being M1 and M2. So in a system, you don't necessarily have just two bodies. You could have very many bodies, right? And each could be mutually interacting. Their mutual interactions find no representation when they are all cemented and stitched together. But then the moment you isolate them, then their mutual interactions appear. The moment you isolate M2 or you isolate M1, then what they're doing to each other gets represented. But when they are together, their mutual interaction finds no representation. Because together, the mutual interaction cancels off. Consequence of Newton's third law. Now, I know it's hot and sticky and sultry and humid, but never mind. You should learn how to withstand this little bit of adversity. It's not too much. This is part of the bigger education. Treat it that way, you'll be able to handle it better. Right? Yes.
So if the given equilibrium, the free body diagram, if there are no, the F was not present, then the free body diagram M2, they are given the same.
Yes.
So when the F is applied.
So which means, I know what you're saying. Think of it like this. Say this was M1, this was M2. And they're resting against each other like this. One more thing that I want to mention is that the contact forces in the form of a normal force is not a mad force. It will not act if not prompted to act, if not required to act. It will act only if it's required, right? When they're acting like this, when they're sitting like this, resting against each other, then M1 is not mad and M2 is not mad. They will not unnecessarily push each other. They will stay quiet like this. There is no interaction, though this does not really represent a contact at all. So normal reaction here is zero. They are on the verge of not being in contact equivalently. That's what it means. They don't exert forces on each other. Like I said, we will down the line learn that normal forces, frictional forces, they are not mad forces. They will act if required. They're self-adjusting, true. They have the leverage to act to their own tune, but then they will act in a manner which is not madhouse, right? So they will unnecessarily not push each other. So they will not exert normal forces on each other. Got me? Reason that, well, there is a force F. There is a force F acting on the system. All right. And essentially, they were together. When this force F acts, they still want to be together. The law of nature is about harmony and not about disharmony. Despite the action of this force F, they still want to maintain congruous relationships. They still want to move together to the extent they could. So what really transpires is that if they are moving together as one single unit to the right, they have a common acceleration. They have a common acceleration A. And if they have a common acceleration A, then realize that, well, look at the free body diagram. There is like a M1G, R1, M2G, R2, right? This A is the effect of F. This is the net unbalanced force. This is the net unbalanced force acting on M1 and M2. Unbalanced forces will produce accelerations, whereas balanced forces will produce deformation. This is an unbalanced force acting rightwards on the system M1 plus M2, producing an effect A. So this acceleration A is like caused by F acting on M1 plus M2. This is the common acceleration of M1 and M2. As far as M2 is concerned, M2 does not have any respect for F, or rather, the normal reaction between M1 and M2, M2 would not even know of F, but M2 still has an acceleration A to the right, M2 still has an acceleration A to the right. If you look at M2 in isolation, then in isolation, you would have to represent the effect of M1 on M2. The effect of M1 on M2 is in the form of a normal reaction N to the right? M1 will exert on M2 a normal reaction N to the right? And then of course there are vertical forces M2G and R2. Now acceleration of M2 is not because of F, it's because of N. But the same acceleration A is caused by N. So then, if I know A, the entire system, the free body diagram of the system M1 plus M2 leads to availability of A. Now this A could be utilized to compute N. Now if I look at the free body diagram of M2, then this A, as far as M2 is concerned, is caused by N. So then N must be equal to M2A. N must be equal to M2A. So N could then be computed. So what is N trying to do? N is trying to produce on M2 the same acceleration A that F is trying to produce on the system, and thereby producing a scenario where M1 and M2 could move together as one single unit with the same acceleration A. How about that, right? So this is how you could have computed the contact force between M1 and M2. Suppose there were three bodies in contact, and let's say to begin with, all of them resting on a smooth surface. Let's say this was 10 kilograms. This was 20 kilograms. And this was 5 kilograms. Right? And I have a 70 Newton force acting on this. If I had a 70 Newton force acting on this, right? And let me call this body A, let me call this body B, and let me call this body C. And I want to compute the forces that A and B exert on each other, B and C exert on each other. Even before I venture into doing that, I look upon these as one single system, one single unit. If they are looked upon as one single unit, then the free body diagram of A, B and C would be this force, along with gravitational forces acting downwards and normal forces from the surface acting upwards, right? This would be the free body diagram of the three put together, right? In this event, what would be the acceleration of the system? Acceleration of the system would be 70 divided by 35, that is 2 meters per second square. The system now has an acceleration 2 meters per second square. Since all three units are moving together, every unit of this assembly has the same acceleration. So now what we could do is, we could draw the free body diagram of B and C. If I have to find what A is doing to B or B is doing to A, it's important that I create a temporary disharmony. I cut them open at this point at their interface. That's when I would know what they're doing to each other, right? That's the only way I would know. When they're together, I would not know what A is doing to B or B is doing to A. I must create a partition here I must create a conceptual partition here to examine what they are doing to each other. So what I might then do is, I might look at the free body diagram of B and C. If I look at the free body diagram of B and C, then on this system, let's say A exerts on B at this interface, a force N1. A exerts on B at this interface a force N1 to the right, a normal force. And that causes B and C to have an acceleration 2 meters per second squared to the right. And of course, there is gravity acting downwards and there is normal reaction acting upwards from the surface on B and C. But then, this N1 could then be computed because N1 is causing 2 meters per second squared to B and C. N1 then you realize is 25 into 2, which is 50 newtons. Total mass 25 into 2, which is 50 newtons is N1. Right? I could have also computed N1 by looking at the free body diagram of A alone. Of A alone, I could have even computed. So, it does not matter which part you take. If I look at the free body diagram of A alone, A, which is like 10 kilograms, acted upon by 70 newtons. Now, if A exerts on B a pushing force N1 to the right, B will exert on A a pushing force N1 to the left. So, B will exert on A pushing force N1 to the left. Right? Under the influence of these two forces, what happens to the acceleration of A? Same, 2 meters per second squared. So, the acceleration of A is like 2 meters per second squared under the influence of a 70 newton to the right and N1 newtons to the left, which means what? N1, which means 70 minus N1 is the net force to the right, and that causes a 2 meter per second squared acceleration on the 10 kg mass. So, that must be mass into acceleration 2. So, N1 then becomes equal to 50 newtons. It does not matter how you compute N1. To be able to compute N1, you would have to dissolve the barrier, but you will have to somehow create a barrier between A and B and look at either A separately or things to the right of A separately to know what they are doing to each other. Clear? So far so good, right? Now, how does one compute the force that B exerts on C or C exerts on B? Well, obviously, you will have to break it open at this point. At this interface, you will have to break it open. Which means, look at the free body diagram of C alone, for example. So, if I look at the free body diagram of C alone, this is like a 5 kg. Then B exerts on C a force N2 in this direction, a pushing force N2 in this direction. And there is gravity acting downwards, there is normal reaction acting upwards, and under the influence of all these forces, there is an acceleration 2 meters per second squared rightwards. So then, what would N2 be? N2 would be 5 into 2, that is 10 newtons. N2 would then be 10 newtons. You could have computed N2 by looking at the free body diagram of B alone or A and B together. What would be the free body diagram of B alone? Let's assume A will exert on B a normal reaction N1 to the right, right? C will exert on B a normal reaction N2 to the left, right? N1 we have already computed. Now to compute N2, one thing I know, the net effect of N1 and N2 is an acceleration 2 meters per second squared computed universally, right? So then we have like a N1 minus N2 equals mass of B, which is 20 into. So if you knew N1, then you could have computed N2 from these considerations. Does it make sense to all of you? Right? Now, coming back to the string. Now that you understand what a free body diagram is, let's get back to the string side of the story. All right. So, like I mentioned to you, a string is is supposed to be an inextensible entity, right? In contrast to its brother, the spring, which is extensible, right? So, if this is a string, for example, this is a string, for example, string AB. And let's say L is the length of the string and M is the mass of the string. L is the length of the string and M is the mass of the string. And let's imagine the string to be uniform, So, its mass per unit length, lambda, mass per unit length is going to be M by L. Mass per unit length is going to be M by L, isn't it? M kgs uniformly spread over L units, giving you mass per unit length lambda is M by L. Okay. Now suppose, and let's say it's resting on a smooth surface. It's resting on a smooth surface and it's being pulled to the right with a force. It's being pulled to the right with a force F. Clear? I then want to compute. So there would be some tension built up in the string. I then want to be able to compute the tension at a point P, x units to the left of B. I then want to be able to compute the tension at P. X units to the left of B. Hey, if I looked at the free body diagram of AB, then at P, the force T would be to the right as well as to the left and will have no consequence and will not appear for computation, right? Because then it will cancel off in pairs in as far as AB is concerned. So then, if you want to compute the force at P, if you want to be able to compute the force at P, then you must cut it open at P. And you must examine the free body diagram of AP or the free body diagram of BP. One of the two would have to be imagined so that the force at P could be unleashed, right? Now, let's look at the free body diagram of the whole thing first. Let's see what this F is doing. Now, if I look at AB, then the tension force at each and every point between A and B would be equal in magnitude, opposite pair of tension forces in both directions, and they would cancel off. So then, the net of all forces horizontally acting on AB would be a single unbalanced force F. Because on AB, tension forces at every point inside AB would cancel off. So this would be the net unbalanced force on AB. What does it do to AB? It produces an acceleration on AB. So the acceleration that it produces on AB is like a F by M. That's the acceleration that it produces on AB, right? F by M. And that's the acceleration of every single unit, every single entity, every single part of this string has the same acceleration A. Okay. Now what I can do is, to know the story at P, I would want to cut it open at P. And when I cut it open at P, I would then want to examine either PB or AP separate, right? So let me look at PB to begin with. Let me look at the free body diagram of PB. If I look at the free body diagram of PB, then at B, there is a force F acting to the right. There is a force F acting to the right at B, right? Now ask PB. PB will tell you that it's being pulled. PB will tell you that it's being pulled by AP. It's being pulled by AP with a force. PB will tell you that it's being pulled by a force T by AP leftward. So the tension at P would be T leftwards. It has to be pulling in character. It must pull PB. And pulling PB would have to be a leftward designation, right? Yes or no? Right. And of course, there is weight of PB acting downwards, balanced by a normal reaction acting on PB. Now, I'm not representing that because in my calculation, in my larger scheme of things, it will not be a required force, right? So, horizontally, these are the only forces acting on PB. Now, under the influence of F and T, what transpires to PB? What happens to PB? It has an acceleration A common with the larger unit. It has an acceleration A common with the larger unit. So, it has an acceleration A to the right. It has an acceleration A to the right. Which means what? From Newton's second law, we have like a F minus T is the net unbalanced rightward force. Net unbalanced rightward force acting on PB. And that must be equal to mass of PB into acceleration of the system, which we've already computed from the free body diagram of the system AB alone, right? A, so we know, is F by M. We just need to be able to compute T. Hey, mass per unit length is M by L. So, what's the mass of X? M by L into X. So, mass of PB is going to be X into lambda. X into lambda, yeah, right? So, mass of PB is X into lambda into A, right? X and then lambda is like M by L is M by L into A, where A we have computed as F by M. F by M, right? And then we have like T given F. T then becomes F into 1 minus X by L. T then becomes F into 1 minus X by L. Yes or no? So, for different values of X, you can compute the tension at different points of the string. I mean, if you put X equal to L, that means you'll get the tension at A, which turns out to be 0. If you put X equal to 0, you'll get the tension at B, which turns out to be F. So, depending on the point where you need the tension, you can plug in the corresponding value of X and arrive at the value of the tension force at point. So, in general, you'll have tension different at different points along the string in general, right? Now, a situation that we account for time and again is the following. Look, in this case, we imagined the string AB to have a certain mass, M, spread uniformly over a length, L. Suppose I said that the string was massless. Again, that's an abstraction. It never happens. But then, good for practical considerations if required, right? So, if I imagine the string to be massless, that means of negligible mass. In the system that we are envisaging, all of the masses are much larger compared to the mass of the string. Then we can ignore the mass of the string. That's when I say that the string, for all practical purposes, is massless. So, if AB had a negligible mass, would you not imagine that PB would also have a negligible mass? And if PB had a negligible mass, then mass of PB is approximately 0. Is approximately 0. And if it's 0, that means the right hand side is approximately 0. Right? Then T becomes equal to F if the string was massless. That means now T has become independent of X. T has become independent of X for a massless string. That means for a massless string, the tension seems to be the same at every point in the string. Tension seems to be the same at every point in the string. Got me? If it had mass, then the tension for different values of X could be computed from these considerations, right? So in a massless string, tension is practically the same at every point in the string. Of course, like I said, it's an approximation. Tension is approximately the same at every point in the string, but it's a good enough approximation. Got me? The direction of the tension at any point will depend on the free body diagram of the entity that you are proposing to draw. I mean, if I drew the free body diagram of PB, then the tension was leftwards. But if I drew the free body diagram of AP, the tension would be rightwards. Now, free body diagram of AP would be what? If I have to draw the free body diagram of AP, there is T at P. AP, sorry. There is T at P, right? But then this T is in both directions, like I said. The direction that you choose at P would depend on whether you're drawing the free body diagram of AP or you're drawing the free body diagram of PB. So if you're drawing the free body diagram of AP, the tension at P would pull AP. And pulling AP means it can't be like this. It will not crumble the string to dust, right? It will pull the string with a force G. Pull the string with a force G, right? So then, what would this T do to AP? This T would be congruous with the fact that all parts of the system have the same acceleration. So the bigger unit AB had an acceleration F by M, and so will the smaller unit AP. So this will have an acceleration A, which is common with the bigger body F by M, right? So then, tension. This is the only horizontal force acting on AP. The other forces are mg downwards and normal reaction upwards from the ground. So then T must be mass of AP into acceleration A, right? AP is of length L minus X. AP is of length L minus X. So the mass of AP is mass per unit length into L minus X, and A becomes F by right? Lambda is mass per unit length. So you can write lambda as M by L. Which is like F into L minus X by L. Same as what we computed earlier, right? So tension at a point in general will exist in both directions. But the direction of the tension that you have to choose will depend on the specific free body that you are attempting to clear. Let's look at some more systems. Suppose I have a mass here. M1 equal to 10 kgs. And there is a string here. And there is another mass here, M2 equal to 5 kgs. And let's say the string has mass 15 kgs and has a length 5 meters, has a length 5 meters. This is the string which has mass 15 kgs and has a length 5 meters. And then this system is pulled up with a force F, which is 30 newtons, with a force F, which is, let's say, 60 newtons. Pulled up with a force F, which is 60 newtons. First of all, what would be the acceleration of the system. What would be the acceleration of the system? There is, let's say this is 600 newtons. 600 newtons. What would be the acceleration of the system? Okay, 600, and then there is a downward force because of Mother Earth. 10 plus 15 plus 5, 30 into 10. Assuming G as 10 meters per second squared, there is a downward force which is like 10 plus 15, 25 plus 5, 30 kgs into 10. That is 300 newtons downwards because of gravity. Because of gravity, right? Okay. Which means now the net force acting on this system, M1 plus string plus the other mass M2, the net force is like 600 minus 300, that is 300 newtons, divided by the total mass, 30 kilograms, which makes it like 10 meters per second squared. Acceleration is 10 meter per second squared. Okay. Next, I want to compute the tension at A. I want to be able to compute the tension at A in the string. So obviously, I will have to cut it open at A. I'll have to cut open the system at A. Either I can look at the system above A to know what's happening at A, or I can look at the system below A to know what's happening at A. Either way, it's going to give me the same result. Okay. Suppose I look at the system above A. Suppose I look at the system above A to know what's happening at A. So, now the free body diagram of A alone, free body diagram of A alone. (10 kgs). There is 600 newtons acting upwards. There is gravity, 100 newtons acting downwards, 10 into 10 acting downwards. And there is tension in the string at A. At A, the tension on M1 would pull M1, so downwards. So at A, the tension as far as M1 is concerned is going to act downwards because it ought to be pulling M1. And pulling M1 means exerting a downward force, right? So at A, the tension is T downwards. Does this summarize all forces acting on A? It summarizes all forces acting on A. We then have like the net of all forces, 600 minus 100 minus T, right? Minus 100 minus T. That must be mass of this, which is 10. Now, this has the same acceleration as the total. All parts of the system have the same acceleration. So, M1 into acceleration, which was 10 meters per second squared of this, mass into acceleration 10, right? Clear? So, then that gives me like G equal to 500 minus 100, that is 400 newtons is the tension at A. Tension at A. Clear? I could have also computed the tension at A by looking at the free body of the system below A. By looking at the free body of the system below A. Let's just do that. Below A, there is M2, which is 5 kgs. Okay. Now, at A, as far as tension is concerned, and the lower part is concerned, tension at A now for this unit, for this segment would act upwards because it has to pull it. And pulling this is like upwards, right? So, direction of tension at A now on this is like T upwards, is like T upwards, right? Okay. What are the other forces? Now, this is 15 kgs and this is 5 kgs. So, 20 kgs into 10, which is 200 newtons. And what does this result in? A net acceleration of 10 meter per second square. So then we have tension minus 200, right? Tension minus 200, that's a net upward force acting on this system. That must be mass of the system. Mass of the system is like 15 plus 5, 20 kgs. Into acceleration, 10 meters per second square. So that makes it T equal to 400 newtons. Same as the number that we computed by looking at the free body diagram of M1 alone, right? Okay. So that's as far as the tension at A is concerned. Okay. Suppose I want to compute the tension at a point B. This length is 5 meters. So suppose this is 1 meter. Suppose I want to compute the tension at B, which is 1 meter below A, which is 1 meter below A. Then I'll have to cut it open at B and either look at the free body diagram above B or free body diagram of the system below B, right? So let me look at what's happening below B, for example, right? Now, as far as this part is concerned, tension at B is going to be upwards or downwards? It's going to be upwards. It has to pull this. It can't push this. Tension can never push any entity. So, tension at B will pull this entity. So, tension at B, let's say, is T1 upwards. Let's say T1 upwards. Now, what are the other forces? Now, this is 1 meter. So, this is 4 meters. Right? And its mass per unit length is like 3 kilograms per meter. 3 kilograms per meter. So this is 4 meters. So this would be 12 kilograms. Right? This is 12 kgs. And this is 5 kgs. So then, because of Mother Earth, 17 into 10, 170 newtons downwards. Does this summarize all forces, external forces acting? And then what must be the effect of T1 and 170? An acceleration 10 meter per second squared upwards. So then we have T1 minus 170 is mass, which is 17 into 10. T1 is 340 newtons. Yes or no? Could I have arrived at the value of T1 by looking at what's happening above B, right? I could have done the same. So let's just do it to get familiar with everything. And above B again, I could have looked at from A to B or B and right to the top. Either way, it's fine, right? So let's say this is B. Now, this is 1 meter, so this will be 3 kgs. This is 10 kgs. There is 600 newtons. Now, this is 13 into 10, that is 130 downwards, Mother Earth. Now, at B, the tension on the upper portion would act downwards because it has to pull it, right? So, it's going to be T1 downwards. Does this summarize all forces for us? All forces summarized? So then we have like a 600 minus 130 minus T1 equals mass of this, that is 13 into 10. So this will give me T1 once again. Yes or no? So T1 could have been computed either from the free body diagram of what's above B or what's below B. Either way, it's fine, right? You get the same value 340 from here also, right? If I had to find the free body, if I had to find the tension at C, I could have, let's say, looked at what's below C, for example. Below C is M2, Below C is M2. At C, the direction of tangent acting on M2 is going to be upwards. It has to pull C upwards, right? T2. There is 50 newtons acting downwards. And the net effect of all this is what was computed universally for the system, 10 meter per second squared upwards, right? This is the effect. The cause is T2 minus 50 is the cause. T2 minus 50 is the cause. And the effect is 5 into 10. T2 is 100 newtons. T2 is 100 newtons. Got me? So, this is how tension forces will operate. This is some basic idea on how to compute tension at various points on a string based on whether the string has mass or it didn't have mass, negligible mass, and so on and so forth. Now, one very important principle which I want to deliver to you in as far as mechanics is concerned is a very special constraint condition, a very special constraint condition. Very important, and it's extremely important. You understand it now and you'll use it with a lot of versatility, with a lot of simplicity as well in very sophisticated situations. One thing. Suppose these were two bodies. These were two bodies. Right? This was their common interface. This is the common normal direction. That is this will be perpendicular to both the surfaces, right? Common normal direction. This is the tangential direction. This is the tangential direction. Now, if both these bodies, let's say this was body A and this was body B. Okay. If both these bodies had a velocity only in the tangential direction, let's say this body had a velocity v1 and this body had a velocity v2. Their velocities were only in the tangential direction and they had no velocity in the common normal direction. Then they would maintain contact. Velocities in the tangential direction would not result in loss of contact. They would still maintain contact. I mean, assuming they are very large and it doesn't run over the edge of this, that's another story. But other than that, they would maintain contact, right? Now, suppose this had a velocity v1, this had a velocity v2 in the common normal direction. This had a velocity v1 and this had a velocity v2 in the common normal direction. Will they maintain contact? No, it's not about v2 is less than v1. As long as v2 is not equal to v1, contact would be lost. I mean, these are two bodies. This is the tangential direction. This is the tangential direction. If the one is moving up or down, their velocities in this direction will not result in loss of contact. But the normal direction would be this. The normal direction would be this. If they had different velocities in this direction, then loss of contact would take place. Along the common normal direction, if their velocities were different, then loss of contact would take place. This will not result in loss of contact. Any relative motion in this direction will not result in loss of contact. But if they had relative motion in this direction, that will result in loss of contact. Yes or no? Which means loss of contact is about having different velocities. I gave you loss of contact in terms of the normal reaction end, right? Now, loss of contact in the kinematic version, in the kinematic point of view. This is the kinematic point of view, right? In the kinematic standpoint, loss of contact is about having different velocities. Having different velocities in the common normal direction is about having different velocities in the common normal direction. Different velocities in the tangential direction or the parallel direction will not result in loss of contact, but having different velocities in the common normal direction will result in loss of contact. Now, I know what he's saying. He's saying, now can you at all have a situation of this kind? He's saying, this has a velocity 5 meters per second and this has a velocity 3 meters per second. Now that situation is not even possible. I mean, can this have 3 meters per second and this have 5 meters per second and still maintain contact? This interface needs to have a certain velocity. इसका माई बाप कौन होगा? ये होगा कि ये होगा? इसका तो कोई माई बाप होना चाहिए. इसका क्या velocity होगा फिर इस interface का? 5 या 3? It doesn't have a माई बाप. Right? So that situation is ruled out. So, different velocities in the common normal direction will result in loss of contact. Which means, to maintain contact, they must have a common velocity in the common normal direction. Yes or no? A necessary condition. And in fact, also a sufficient condition. Assuming, there are no other factors. In order to maintain contact, this is the common normal direction. If this had a velocity v, this must also have the same velocity v in the common normal direction. That means their relative velocity in the common normal direction must be 0. Write down. For two bodies to maintain contact, their relative velocity in the common normal direction must be 0. Right? And not just that. In fact, if they had a common velocity at a certain instant of time and they have to maintain contact, and let's say these two A and B were accelerating, they need to have the same acceleration also in the common normal direction. Because if there was a difference in the acceleration, their velocities after a while would become different in the common normal direction and parting would result. Right? So to maintain contact and so as to maintain a zero relative velocity along the common normal at all instants of time, they must also have a common acceleration in the common normal direction. That means their relative velocity in the common normal direction must be zero, their relative acceleration in the common normal direction must be. That's a kinematic requirement for two rigid bodies to be in contact. Two rigid bodies, by the way. If they were not rigid, then what I have said will not be true. I mean, if this would deform, then they don't need to have a common velocity or a common acceleration to maintain contact, because this would wax and wane. So this is the condition for two rigid bodies to maintain contact at all times. Their relative velocity and therefore their relative acceleration in the common normal direction must be zero. They must have the same velocity and the same acceleration in the common normal direction. They can afford difference in velocities or difference in accelerations in the tangential direction or the parallel direction. Sounds all right? Yes. हाँ, पार्टिंग तो हो गई. I answered this question. That cannot happen. If V1 is greater than V2, suppose V1 is 8 meters per second and V2 is 2 meters per second, then what would be the velocity of this if they were to be together? 8 or 2? Can't say. So this is not a possibility, right? This cannot happen. Simple? So, suppose there was a rigid body like this. And there was another rigid body. This was A and this was B. The common normal direction. And let's say the velocity of A was VA like this. Velocity of A was VA like this. A is a rigid body. Velocity of A is VA like this, making an angle alpha with the common normal, and the velocity of B, let's say, was VB like this, making an angle beta with the common normal, right? Now, for them to maintain contact, the velocity of A along the common normal must be equal to velocity of B along the common normal. That's the requirement, right? What's the velocity of A along the common normal? VA cos alpha. So to maintain contact, VA cos alpha, velocity of A along the common normal must be equal to velocity of B along the common normal, that is, must be equal to VB cos beta. That's when they, right? Make sense? Right? And what I have said of velocities will also be true of accelerations. That means, suppose the acceleration of A was A1 making an angle alpha, and the acceleration of B was A2 making an angle beta with the common normal. So again, their accelerations along the common normal must be the same. That means A1 cos alpha then must be equal to A2 cos beta. A1 cos alpha then must be equal to A2 cos beta to maintain contact. Sounds alright? So to maintain contact, their velocities and acceleration along the common normal must be the same. That means their relative velocities and relative accelerations along the common normal must be 0. This is an extremely useful stuff. Extremely useful stuff. Now, one entity that you're going to encounter time and again in mechanics is the inclined plane entity, the inclined plane. Say this is an inclined plane and making an angle theta with the horizontal. Inclined plane making an angle theta with the horizontal. And let's say the inclined plane is fixed. You can glue the inclined plane to the bottom, right? Let's say the mass of the inclined plane was capital M. Mass of the inclined plane was capital M, and there was small m resting on the inclined plane, and let's say the surface of the inclined plane was smooth. Let's say the surface of the inclined plane was smooth, right? Now, let me draw the free body diagram of small m, capital M, and small m plus capital M, right? Now, as far as small m is concerned, this is small m. The forces acting on small m, there are only two forces acting on small m. There is mg downwards because of Mother Earth, vertically downwards. This angle is theta. There is mg acting downwards. And the surface, the inclined plane surface exerts on small m a normal reaction n upward. Normal reaction n will always push, will never pull. So it's going to push, would attempt to push m perpendicular to the surface of the plane, right? Now, one may decide to resolve the two forces depending on the situation, but just to give you a geometrical disposition which is reusable, realize that this makes an angle theta with the horizontal. This surface makes an angle theta with the horizontal. So a perpendicular to it will make the same angle with the vertical. If a certain line makes an angle theta with the horizontal, then perpendicular to that line will make the same angle theta with the vertical. Would you expect that? Right? So if this makes an angle theta with the horizontal, a perpendicular to it would make an angle theta with the vertical. Right? If one decides to resolve, you can choose, if this angle is theta, then this angle will also be theta. If you decide, you can resolve mg as mg cos theta perpendicular to the plane and mg sin theta parallel to the plane, right? If one likes, one could resolve mg cos theta perpendicular to the plane and mg sin theta parallel to the plane. If you want, it's parallel to the plane. Right? Now, the the body resting on the inclined plane, is moving down the plane, it's not losing contact with the plane, That means their accelerations, this is the common normal direction, that means the acceleration of this body in the common normal direction must be the same as the acceleration of the plane in the common normal direction. Hey, but the plane is fixed. So what's the acceleration of the plane in the common normal direction? 0. Acceleration of the plane in the common normal direction is 0. So acceleration of the body in the common normal direction must be 0. If the acceleration of the body in the common normal direction is 0, that means the net of all forces in the common normal direction acting on the body must be 0. So since the body has no acceleration in the common normal direction, can I not say that n minus mg cos theta must be 0? N minus mg cos theta must be 0. Clear? Now, what's the only unbalanced force acting? Mg sin theta. And what does this mg sin theta do? It produces an acceleration parallel to the plane, a parallel on the body. It produces an acceleration a parallel to the plane on this. That means mg sin theta is the only unbalanced force producing an acceleration a parallel to the plane, which is a parallel, right? That means a parallel is g sin theta. That means if the plane is fixed, then the acceleration of m is g sin theta parallel to the plane, So that's the story of this body, small m, resting on the plane. There are only two forces, n and mg. Together, they produce a net acceleration g sin theta parallel to the plane if the plane and the body have to maintain contact and if the plane is fixed. Alright. Now, as far as the plane is concerned, free body diagram of the plane. There is mg downwards. Weight of the plane, Mother Earth, downwards, mg. There is normal reaction, r, from the ground upwards on the plane, right? And if capital M, that is the plane, exerts on small m, or normal reaction n like this, small m would exert on capital M an equal and opposite n, right? Right? So on capital M, this is the common normal direction. So capital M exerts on small m n like this. So as a consequence of reaction, small m would exert on capital M n like this. Yes or no? Right? And this direction, like I said, this direction makes an angle theta with the vertical. The common normal direction makes an angle theta with the vertical, right? Then there is like a theta vertically opposite angles. N, then you might want to resolve as n cos theta vertical and n sin theta horizontal. N could be resolved as n cos theta vertical and n sin theta horizontal. N cos theta vertical and n sin theta horizontal. Okay. Now, in the plane is fixed. So, net of all forces in the vertical direction must be 0. Which means, in the vertical direction, the forces are n cos theta plus capital Mg minus R, that's 0. Now tell me, there is an unbalanced n sin theta. Who takes care of that? How's n sin theta handled? After all, it's fixed. That means it couldn't get accelerated under the influence of n sin theta. There must be something that must be countering n sine theta. Realize that if it's glued to the ground, then the glue would exert maybe adhesive forces to counter n sine theta. So the glue might exert a force Fg right like this to take care of n sine theta. Or if it was resting against a wall, then the wall will exert a n sine theta on the inclined plane rightwards to counter this n sine theta to keep the inclined plane fixed. Got me? So far so good? Now, this is the raw story of the simpler version of the inclined plane, right? One mild modification to this. Again, in this, I've regarded everything to be smooth. I will continue to regard things to be smooth for a while. Now, the small variation that I propose here is that I allow the inclined plane to move. The inclined plane is now allowed the flexibility to move. It's not fixed. Suppose the inclined plane can move on the horizontal surface, which also is frictionless. It's not glued to the surface or it's not held by a wall, right? Let's see what transpires in the event the inclined plane is allowed the flexibility to move, right? Please pay attention. This has to be understood right now, right here, alright? Even if you are very tired, you must make sure that you regain your concentration. It's a simple stuff that I am communicating to you and you should be able to understand it, right? If you don't, ask me to reiterate that stuff, okay? Very simple stuff. In all probability, you will understand that. But this was the fixed inclined plane. Let's look at the same story for a movable inclined plane, right? Movable plane. Now, like before, the common normal direction is this. This is the common normal direction. The forces acting on small m, there are only two forces acting on small m. There is gravity, mg acting downwards. This is the vertical direction, this is vertical. And the normal reaction that the inclined plane exerts on m is n outwards like this, right? This is the summary of all forces acting on small m, right? This angle is theta, this angle is theta. So this angle will also be theta, vertically opposite, right? You might choose to resolve mg perpendicular to the plane and parallel to the plane. So mg resolved perpendicular to the plane would be like a mg cos theta. Mg resolved parallel to the plane would be a mg sin theta, right? So which means mg could be replaced by a mg cos theta like this and a mg sin theta like that, right? Now, the inclined plane. Now I am imagining the inclined plane to be movable yet frictionless everywhere, right? On this surface as well as this surface, there is no friction, right? Now, the inclined plane exerts on small m a normal reaction like this. So, small m would exert on the inclined plane a normal reaction n this way. About that, right? So, on the inclined plane, this is the common normal direction. Consequence of Newton's third law. An equal and opposite n would act. An equal and opposite n would act. This angle, like we have seen, is theta with the vertical, right? This is theta. Now, n could be resolved as n cos theta and n sin theta. Right? And then there is weight, mg acting downwards. Weight, mg acting downwards. And there is a normal reaction R acting upwards from the ground. Does this summarize all forces? Now, R, like I said, is a self-adjusting force. It will act in a manner so as to produce vertical equilibrium. So then, n cos theta plus mg minus R will be 0. In the vertical direction, the inclined plane will have no acceleration, right? So we have like a n cos theta plus mg minus R is 0. That's the story in the vertical direction. Now, in the horizontal direction, realize that there is an unbalanced n sin theta, right? What does this n sin theta do? It produces an acceleration A in the leftward direction on the inclined plane. So, the inclined plane, while this goes down, the inclined plane moves leftwards with an acceleration A. So, then, if capital M is the mass of the inclined plane, can I not say that n sin theta is capital M into A? Right? So far, so good. Now, come back to this body. We've represented forces, but we have not written equations for this, right? Suppose this body has an acceleration in the common norm while it slides down and the inclined plane moves leftwards. See, you imagine this to have an acceleration A1 perpendicular to the plane and an acceleration A2 parallel to the plane. In this case, n will no longer be mg cos theta if the plane is fixed. If the plane is movable, n will no longer be equal to mg cos theta. You'll see that in a short while. I'll show you why. See, I claim that A1 will no longer be 0. In the earlier case, when the plane was fixed, A1 was 0. But now I claim that A1 is not 0. The acceleration component of m in the perpendicular direction is no longer 0. I claim that. Why? It's based on what I discussed a while ago. This was theta. Small m. The acceleration, this was the common normal direction, right? The acceleration of the inclined plane, like we saw was A leftwards. Now, in the common normal direction, if they have to maintain contact, right? To maintain contact, the acceleration of the inclined plane in this direction must be the same as acceleration of small m in the common normal direction. That means, now, look at this. This angle. This is the horizontal, so this angle is theta. This angle is theta, right? Corresponding angles, right? Theta. That means, what's the acceleration of small a in the common normal direction? What's the acceleration of the inclined plane? A. It's a leftwards. What is its component in the common normal direction? Component of acceleration of the inclined plane in the common normal direction is, like you can see, is a sine theta, So what would be the acceleration of small m in the common normal direction? A sine theta. Acceleration of small m must also be a sine theta. Why? Because that's a requirement for maintenance of contact. So that means, what should this A1 be? A capital A sine theta. This A1 must be capital A sine theta, and therefore not 0, and therefore not 0, unlike the fixed inclined plane. That means A1 must be equal to A1 acceleration of small m in the common normal direction. So I know the acceleration of small m in the common normal direction. That's A sine theta. That's A sine theta. A1 then turns out to be A sine theta. A sine theta, yes or no? Okay. Now, in this direction, if I asked you to apply Newton's second law in this direction, what would you say? Can I not say mg cos theta minus n for this body small m, free body diagram of small m? Can I say that mg cos theta minus n must be small m into A1? Could that be said? Right? Deploying Newton's second law to small m in the common normal direction, can I say that mg cos theta minus n must be m into A1? Right? Where what is n? N is capital MA by sine theta. N is capital MA by sine theta. Mg cos theta minus n. N, like you see here, is capital MA by sine theta. And that must be equal to MA1. That must be equal to MA1, M into A sine theta. Right? So which gives me, A is the acceleration of the inclined plane. A is the acceleration of the inclined plane. So can I say that A into M sine theta plus capital M by sine theta, mg cos theta, just by collecting terms suitably, bringing this here, taking A common, M sine theta plus capital M by sine theta is mg cos theta, right? Or acceleration of the inclined plane is mg cos theta sine theta by m plus small m sine square theta. That would be the acceleration of the inclined plane. Mg sine theta cos theta by capital M plus small m sine square theta. That's the acceleration of small m. Right? Now, so if I know capital A, don't I know A1? A1 is capital A Sine theta. So I know A1 also. Because I know capital A. A1 would be capital A sine theta, right? Now, in this direction, if I have to write the force equation for small m, what would be the force equation for small m in this direction? mg sine theta would be ma2. mg sine theta would be ma2. Right? So, A2 then turns out to be G sine theta. A2 then turns out to be G sine theta. Right? So then, for suppose this was the y direction and this was the x direction. Suppose this was the y direction and this was the x direction. What would be the acceleration vector of small m? Acceleration vector of small m is what? A2 I cap plus A1 j cap. A2 I cap plus A1 j cap. Where A2 we have computed G sine theta, A1 capital A sine theta, where capital A we have arrived at. Mg sine theta cos theta by capital M plus small m sine square theta. So that's the acceleration vector of small m. Its component in this direction we know, its component in this direction we know. So we can play around with it and arrive at the total. So what will be the total acceleration of small m? Root a1 squared plus 2 squared, as seen by a person on the ground. As seen by a person on the ground. Are you okay with this? You've absorbed this part? Have you actually understood this? Achha, theek. Just give me one moment. What did I say was the condition for contact between two bodies? Their accelerations in the common normal direction must be the same, right? This was the inclined plane. The inclined plane had an acceleration a leftwards, and this small m had an acceleration which I said was like a a1 perpendicular to the plane and a2 parallel to the plane. Right? This angle was theta, this angle was theta. So this is the acceleration of small m perpendicular to the plane. This is the total acceleration of the inclined plane. For them to maintain contact, do you realize that they must have the same accelerations in the common normal direction? In the common normal direction, what's the acceleration of small m? A1. What's the acceleration of capital M? That's the component of A in this direction, which is A sine theta. Right? So just equating their accelerations along the common normal direction, we will arrive at maintenance of condition for maintenance of contact between the two bodies. Right? So if you have actually understood all that I said from the beginning to the end today, then you've traveled a respectable distance. You would have bred decent familiarity with free body diagrams, simple application, simple conditions for maintenance of contact between two rigid bodies, how they maintain contact, and we could readily apply that to a movable inclined plane, arrive at the acceleration of the inclined plane and the total acceleration of small m moving down a moving inclined plane, right? Fair enough? This much for today.